Hello everyone, welcome to the class. So today we are going to discuss isomerism. First of all, what is isomerism? So two or more, two or more compounds with same molecular formula, two or more compounds with same molecular formula but different physical and chemical properties. Physical and chemical properties. Such compounds are known as isomers, and the phenomenon is known as isomerism. Phenomenon is known as isomerism. अब जो isomerism है, this is of two types. First one is structural isomerism, and second one is stereoisomerism. Stereoisomerism. First of all, we will discuss structural isomerism. So if we have to define structural isomerism, so basically when two or more compounds with same molecular formula but are of different structures. What do we mean by different structure? That is different arrangement of atoms. Different structure means different arrangement of atoms. Arrangement of atoms within the molecule. Within the molecule. Such organic compounds are known as structural isomers of each other. These are structural isomers of each other, and the phenomenon is known as structural isomerism. So let us discuss different type of structural isomerism. First of all, we have chain isomerism. Chain isomerism, which is also known as nuclear isomerism. So basically, in case of chain or nuclear isomerism, two or more organic compounds which are with similar molecular formula, but there is difference in arrangement of carbon atoms within the molecule. Difference in carbon atom means different arrangement of chain. So basically, same molecular formula but different arrangement of carbon chain. If we look at the example, So here we have butane. This is butane. And this is isobutane. Let's count the number of carbon atoms. So here we have 1, 2, 3, 4. 4 carbon atoms. Similar goes here. Number of carbon atom is 4. Let's count hydrogen. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Similarly 1, 2, 3, 4, 5, 6, 7, 8, 9 and 110. As a single carbon atom can make maximum of 4 bonds. So here we have C4H10. Both of these molecules are of similar molecular formula, but the arrangement of the carbon atom is different. That is why these two are chain isomer of each other, and hence showing chain isomerism. Next one is position isomerism. Position isomerism. Position isomerism is when two or more organic compounds are of same molecular formula, but a different position of multiple bond or a functional group. Position of multiple bond or functional group if is different in different molecules, but those molecules are of same molecular formula, then we can say the isomerism possessed by those compounds will be position isomerism. Let's have a look at the example. So first of all, we have but1ene. This is but1ene, and this one is but2ene. This is but2ene. Let's have a look at the molecular formula. So there are 4 carbon atoms in this. Similarly, in this second one we have 4 carbon atoms. Let's count number of hydrogen atoms. 1, 2, 3, 4, 5, 6, 7, 8. C4H8. 1, 2, 3, 4, 5, 6, 7, 8, 9. Sorry, 1, 2, 3, 4, 5, 6, 7 and 8. So the molecular formula is same, C4H8 in both molecules, whereas the position of double bond is different. So this is 1, 2, 3, 4. This is but1ene. The position of double bond is first, whereas in this case, second example, 1, 2, 3, 4. This is but, position of double bond is 2, but2ene. So these two are position isomers of each other, as the position of double bond, that is multiple bond, is different. However, the molecular formula for both the compounds are similar. Let's take another example, that is this. Let's have a functional group OH. If we count down the number of carbon atoms, so number of carbon atoms are 1, 2 and 3. This is C3. Hydrogens are 1, 2, 3, 4, 5, 6, 7, H7OH. 1, 2, 3, 3 carbon atom. Number of hydrogen atoms are 1, 2, 3, 4, 5, 6 and 1, 7. C3H7 with the OH. So the molecular formula in both of the compounds is same, whereas if we name these, so numbering start from here 1, 2 and 3. So the first compound is prop, single bond in OH at first position, then 1 ol. Whereas in the second compound, this is 1, 2, 3, number of carbon atoms in main chain is 3, so prop, single bond, that means ane, whereas the functional group OH is present at second carbon, then it's 2 ol, propane 2 ol. So both of these are examples for position isomerism. Let's move on to next, which is functional isomerism. Third one is functional isomerism. So two or more compounds with same molecular formula, but different functional groups, are known as functional isomer of each other. Let's have a look in the example. So first of all, we have, first example is, let's number it, it's alcohol and ether. So the general formula would be CnH2n plus 2 with the O. Let's say we have CH3 CH2OH. This is eth, single bond ane, and alcohol, that is ethanol, whereas it can be rewritten as CH3OCH3. This is dimethyl ether, or as per IUPAC naming, this is methoxymethane. Both of these compounds are of different functional groups. This is alcohol and this one is ethers, whereas the molecular formula is C2. Both of compounds are containing only 2 carbon atoms, whereas 6 hydrogen atoms and a single oxygen. That means these two are functional isomer of each other. Next one is carboxylic acids and esters. Carboxylic acids and esters. The general formula would be CnH2nO2. We need not to learn the general formula, whereas it will be easier to write down 2 different isomers if we know the general formula. So carboxylic acids and esters, let's say we have acetic acid, and this one is ester. IUPAC naming is ethanoic acid. The second one is methyl methanoate. This is methyl methanoate. This is carboxylic acid, and this is ester. This one is ester. Next example is aldehyde ketone unsaturated alcohols, and even unsaturated ethers, General formula will be CnH2nO. So if we look at the example, let's say we have acetone, number of carbon atom is 3, hydrogen is 6 and with a single O. We have CH3, CH2, C double bond O and a H. Number of carbon atom is 3, number of hydrogen atom is 6 and a single oxygen. Then CH2 double bond CH, single bond CH2 and a OH. Again number of carbon atom is 3, hydrogen is 6 and a single O. CH2 double bond CH, single bond oxygen, and then CH3, C3H6O. So first one is ketone, as the C double bond O fragment is directly connected to two different carbons. This one is ketone. Second one is aldehyde, as C double bond O fragment is connected to at least one hydrogen. This is aldehyde. Next is alcohol. However, the organic chain, main chain is doubly bonded. That means this is enol or unsaturated alcohol. This can be written as unsaturated alcohol. Next one is with O, which is directly connected to two different carbons, and the main chain is doubly bonded. That means this is unsaturated ether. So all of these are functional isomers of each other. Let's have a look to the next example, which is, I think this is example number 4. Aromatic alcohols, then phenols and ethers. These are also functional isomers of one another. So the example is like benzyl alcohol, benzene directly attaching to CH2 fragment, then OH. This is benzyl alcohol, that is aromatic alcohol. It can be written as OCH3. Number of carbon atoms are equal, number of hydrogen atoms are equal, and only one oxygen is present in both the compound. This is, however, is an ether. Common name is anisole. This is benzyl alcohol. It can be written as CH3 with the OH. Now, as benzene is directly attaching to the OH group, that means this is a phenol fragment. The common name is orthocresol. So all of these are functional isomers of each other, as each one of these containing similar molecular formula, but one of them is aromatic alcohol, other one is phenol, and the last one is ether. Let's move on to next, which is primary, secondary and tertiary amines. So we have CH3, CH2, CH2 and NH2. As nitrogen is directly attaching to only one carbon, this is primary amine. It can be rearranged as CH3, CH2, NH with the CH3. As nitrogen is directly attaching to two different carbons, the amine present is secondary amine. If nitrogen is directly attaching to three different carbons, as CH3, CH3 and a CH3, then this is tertiary amine. We can mark it as NH2. This is primary. If we have an H, then this is secondary. if we have only nitrogen present attaching directly to 3 different carbons, then this is tertiary amine. Hopefully you are understanding. If there is any doubt at your part, you can just comment down. Next one is metamerism. Next one is metamerism. So in metamerism, the molecular formula again of 2 or more compounds are same, but the number of carbon atoms, same molecular formula, but number of carbon atoms on either side of functional groups are different. Number of carbon atoms which are present on either side of functional group are different, but the molecular formula is same. Then such isomers are known as metamers to each other. Such molecular compounds are known as metamers to each other, and the phenomenon is known as metamerism. Let's have a look into the examples. First one we have CH3, CH2, O, CH2, CH3. CH3, O, CH2, CH2, CH3. Both of these consist of 4 carbon atoms. Hydrogen atoms are 10 and a single oxygen. Whereas number of carbon atoms, here we have 2 on either side, here we have 1 and 3. Let's have a look into another example. Let's say we have a ketone. This is a ketone. And this is a ketone. So basically number of carbon atoms, here we have 2 carbon atoms around a functional group. Here we have 2 carbon atom around a functional group. Here we have 1 carbon atom and 3 carbon atom around a functional group. However, the molecular formula is C5 H10 and a O in both of the cases. Okay. Next one is tautomerism. Next one is tautomerism. Tautomerism is a special type of functional isomerism. It is a special type of functional isomerism in which same molecular formula but different functional group. So it looks like it is a functional isomerism, but the thing is 2 isomers. So basically in case of tautomerism, 2 tautomers are in equilibrium with each other, and are interconvertible convertible via transfer, or we can say that via rearrangement, via rearrangement within the molecule, within the molecule. So we will see rearrangement within a molecule, and hence it will convert into different molecule which is of different functional group. Let's have a look into the examples. First one, we have a diode system. Diode system. A diode system is one in which where involvement of 1,2 migration. The migration of a group or of an atom taking place from first carbon to the second carbon atom, or first atom to different atom. Those atoms may not be carbon but might be another atom. Let's say it could be a nitrogen, as it is in example. That is, let's say we have a hydrogen cyanide. It can be converted into hydrogen isocyanide, as this hydrogen will shift from first carbon atom to second atom, that is nitrogen. So this is diode system in which 1,2 migration is taking place. More importantly, we have triad system, triad systems, in which we will study keto-enol tautomerism. Keto-enol tautomerism. In case of triad system, there is 1,3 migration. Here we have 1,3 migration. Here we have 1,3 migration. Okay, if we look at the example, so we have CH3 C double bond O with the H. We can write this hydrogen as representing as a single bond, so that we can look at the migration easily. So basically this bond is going to shift at oxygen, as oxygen is more electronegative. This hydrogen carbon bond is going to shift in between carbon carbon, and this hydrogen is now electron deficient, as its electron being shifted towards carbon carbon single bond, and as there is transfer of carbon double bond oxygen pi electrons to the oxygen, so oxygen is now electron rich. So this hydrogen is going to attack on oxygen. So basically what are we expecting is CH2 with a double bond, carbon with the OH and a H. So basically this transfer of hydrogen from first carbon atom to third atom, which is oxygen here, 1,3 migration. This is keto-enol tautomerism. As in the first compound we are with keto group, this is keto form. However, in case of product, there is presence of a double bond, that is ene, and a alcoholic functional group, that is enol. This is enol form. So basically in keto-enol tautomerism, the equilibrium will remain dominantly towards keto form, as keto form is of greater stability due to greater carbon oxygen bond strength, whereas in case of carbon carbon double bond, the strength is not that much. That is why in case of enol form the stability is less, whereas in case of keto form the stability is comparatively more. Lastly, let's look at the ring chain isomerism. Last one is ring chain isomerism. So basically, two or more different functional groups, not functional groups, organic compounds are of same molecular formula, but one is in ring form and another one is in chain form. So basically, two different compounds of similar molecular formulas will be in chain form and in ring form. Let's have a look into the examples. So first example we have CH3 CH double bond CH2. This can be written as in a cyclic form as cyclopropane. This one is prop 1-ene, or can be written as propene, and cyclopropane. If we look at the molecular formula, so here we have two hydrogen. The propene is C3H6. This one is C3H6. So molecular formula is same, whereas one of the isomer is in ring form and another one in chain form. So this was all about structural isomerism. Let's move on to stereoisomerism. Next one is stereoisomerism. Before proceeding towards stereoisomerism, let's look at a question. Comment down how many number of chain isomers are possible for butane, for N-butane. Number of possible chain isomers along with their respective IUPAC naming. So this is the question for you. Next one is stereoisomerism. In case of stereoisomerism, two or more isomers having same structural formula or molecular formula, but different relative arrangement of atoms or groups, in space. So in short, we are talking about spatial arrangement. arrangement. We are talking about spatial arrangement of atoms in two different isomers. So such isomers are known as stereoisomers, and the phenomenon is known as stereoisomerism. So basically there are two major stereoisomerisms. First one is geometrical, which is also known as cis-trans isomerism. Cis-trans isomerism. And second one is optical, which is also known as DL, small d, small l isomerism. So in case of geometrical isomerism or cis-trans isomerism, this isomerism comes into exists due to restricted carbon double bond carbon rotation around, due to which two different arrangements are possible. Two different arrangements, that is cis and trans. Two different arrangements are cis and trans. So basically, let's say we have a C double bond C fragment. Let's say there are first, second, third and fourth, these four positions. So if we have to designate cis, so cis form will be if same group at 1 and 2 or 2 and 3 or 3 and 4 or 1 and 4. So such arrangements would be cis, whereas in case of trans, if same group or atom is present at 1 3 or 2 4. There are only two cases in case of trans. If we look at optical isomerism, exists due to the rotation of plane polarized light by the compound in either right side or left side, either right side or left side, on the basis of which we will get dextro and levorotatory compounds. Either we will get dextrorotatory or we will get levorotatory compound. Dextrorotatory compounds are those which are going to rotate the plane polarized light to the right side, and in case of levorotatory compounds would be those in which the plane polarized light rotated by the organic compound will be on left side. These D and L isomers are experimentally determined, so there is no direct trick to learn that this specific compound will be dextrorotatory or levorotatory. So this was all about isomerism. If there is any doubt at your end, kindly let us know. Thank you.